Good morning. So now we start our discussion on image formation. So in the previous lecture, we discussed about how many steps are there while the image formation at the sensor end. Okay, like when the, the energy that is radiated or transmitted from the source, when that energy reaches to the sensor, then after sensing that energy, what are the further steps through which a DN number is generated corresponding to a particular ground resolution cell? So, is there any doubt in this discussion? So, if there is no doubt, then further we discussed about in detail how analog to digital converter work. Okay, so we are discussing the processing at the sensor. Okay, so from a ground resolution cell, the total upwelling radiance, okay, that falls under the FOV, field of view. We call it IFOV. It is instantaneous field of view. So in this IFOV, the total energy that is collected, somewhere here we have the sensor. I will further explain in detail what is a schematic. So this is the optical part. So through the optical part, energy is concentrated at the sensor. Okay. So let's say the sensor sends total energy E that is coming from the ground resolution cell, as well as some scatters from the atmosphere that also falls in IFOV of the sensor at that particular time. Okay, so total energy E that is collected. How a digital number is assigned corresponding to this energy component, how digital number is assigned. Okay, and finally, what is there once the image is acquired? If you see the soft version of the image, so there is XY position of this ground resolution cell. What is the planimetric location? And corresponding to this XY location, there is a DN number. Okay, and that DN number is generated corresponding to the total energy that is sensed from that particular ground resolution cell. Okay, and when we talk multispectral sensors, okay, multispectral sensor or hyperspectral sensor. In both cases, we have more than one band. Okay, so in both sensors, there are more than one bands. So we have a many channels. Like in this case, I talk about one channel. One channel means one spectral band. Similarly, we have a second spectral band, third onward. Okay, and so in that case, like please wait. Okay, so when we have more than one band, so in that case, at the sensor end, there are many channels to receive the energy coming from the ground resolution cell. So that architecture at the sensor end we'll see later on. The first objective over here is to discuss how analog to digital converter work. So I have already discussed over here in the previous lecture. In case of A to D converter, if you see in this diagram, so on the independent axis, we have the voltages. And while on the dependent axis, that is y-axis, we have a digital numbers. So again, I would like to discuss that part over here. So let's say we select a particular area, okay, and that area is being imagined using a sensor system, okay, and let's say the total area that is being imagined is 5 kilometers square. Okay, so that is 5 kilometers square area, and the spatial resolution that I talked, like spatial resolution is defined in terms of if the ground resolution cell has a square shape, okay, then size, the spatial resolution is determined by the length of a side. Okay, so if that length is m over here, and we assume that spatial resolution, that is length of a side, in case of a square shaped ground resolution cell, if it is 1 meter, okay, so in that case, how many ground resolution cells are present in that 5 kilometer square area? Any of you can respond.
Sir, 5 into 6.
So it will be simply the total number of ground resolution cell or picture element. There are different naming convention for that. They are equal to they are 25 into 10 to the power 6. Fine. Now there are 25 into 10 to the power 6 ground resolution cells, and by using single channel this sensing system, single channel sensing system is there is only one band. Okay. So in that case, all 25 cross 10 to the power 6 ground resolution cells are sensed individually.
Sir, one doubt is there, sir. Sir, why this 5 into 5, sir?
Mhm.
Sir, why we are doing 5 into 5 into 10 power 6? We should use 5 into 10 power 6 divided by 1 meter square only, na?
Yeah, just no need to keep 5 over here. It's 5. Correct. It's 5 in 10 to the power 6. Okay. So for each individual cell, a unique energy is sensed by the sensing system. Fine. So we can say that we can use EI, where I is the index and I represent 1 to 5 into 10 to the power 6. Fine. So corresponding to each picture element, there is a unique energy. But there is a possibility, like let's say that area is mainly populated by 3 major classes. They are vegetation, the first, then a water body. Let's say a river channel is passes through that area. And a third could be its soil. So 3 major classes are present in this area, 5 kilometers square. If we consider the ground resolution cell corresponding to vegetation, then you will see that if we take the difference between two energy components which are from the separate ground resolution cell, but they belong to vegetation, you can notice their differences may be very less. Okay? Let's say if they are coming delta E, so delta E value could be quite less. Okay? It will be quite less because vegetation, they are the vegetation. It means in a given in the selected channel, because I am discussing considering the single channel sensing system. Okay? So there is only single band is used. Okay. So let's say that band is utilizing, let's say it is around 0.7 micrometer. Okay. It's 0.7 micrometer means it is around red band. This is for example. Okay. So in the given band, when you see the spectral signature of vegetation, okay, there may be variation within the class, like a type of vegetation may be changed. Okay, due to that, you may notice the differences in the energy between the different ground resolution cells which are from the vegetation, but due to the intra vegetation changes, the energy component might be different. But if you take the difference, that is not much significant. Okay, so delta E can be very less. So what we want, like, let's say if we are only interested in to by using the images which are acquired by the sensing system, if let's say we are interested to map the vegetation only, we are just want to categorize the vegetation class. Okay, then in that case, why we want to identify each and every this ground resolution cell which are from the vegetation differently, though energy components are different but with a slight variation. So we need to design a system, okay, through which we can neglect these differences, and we assign a certain parameters which represent uniquely all the vegetation ground resolution cell. Representing uniquely means EI and EI plus 1, they are given the same number. Okay? So we need to design a system through which that difference can be neglected. Okay, and all energy components which are vary with very slight difference, they are they are assigned a same kind of I'd say they are assigned same kind of information, I can say. Okay, they are assigned the same number. Similarly, if you see the water body, okay, so water body spectral signature is different compared to vegetation in the selected spectral band, that is in the red band. Okay, so energy component from the ground resolution cells which are from the water, they are different compared to vegetation. But let's say if you do the comparison among the ground resolution cells which are from the water body, obviously with a slight difference in water quality or water characteristic, the energy components may change. Okay, so you can notice the energy differences between the ground resolution cells from the water body, but the difference is very less. They are different with very slight variation. So again, we can assign them the same number. Why to assign a different numbers with a very small change if we are only interested in to delineate a water body in the image? Why we want to go such level of detail? Okay, but see, if really we want to we are interested in to uh, identify the subclasses of water, then in that case we need to assign different numbers. If we can notice, like, okay, among the water bodies ground resolution cells, just we see that we can divide into two part. Okay, the energy which is lying in the first part and energy which is lying in the second part. Like if I plot graph over here, I am only considering the energy components from the ground resolution cells from water. Okay. Let's say EW1 if the water body that is that is there in the area, if that water body characteristic is uniform, then in that case, if you plot the energy component, you plot the histogram of the energy component, you will get like this. Okay, there is a peak. This is the frequency. There is a peak around which, in a very narrow difference in the energy, all the energy components from the water body is concentrated. Okay, like if I draw the area over here, and that is imagine, and we are discussing about that area. Okay, and a water channel is passes through that area, and then uh, around the water channel, you can assume that there are the soil, they are barren land, and somewhere here there are the trees, even some agriculture field could be assumed. Okay, now let's say if the characteristic of water is uniform, water characteristic is uniform throughout this channel. Okay, then you will get this type of histogram for energy components which are from these ground resolution cells. From the water channel. But let's say if we can assume that the turbidity level changes, like up to this location, the water is clear, but after that, uh, the water is turbid. In that case, what will happen? These ground resolution cells uh, are having a same kind of energy, while the second part where water is turbid, for that part the energy component will be different. Okay, and in which band we are doing the imaging? We are doing imaging in around the red spectral band. It's a red band, and it is 0.7 micrometer, around 0.7 micrometer. We design the sensor within a spectral band. Okay, not at a particular wavelength. So 0.7 micrometer is a central wavelength of that spectral band. We call it red band. I have a query based on the previous discussion, like we detailed analysis we had while discussing the spectral signature of water and how it differs with respect to the turbidity level. If I would like to draw a histogram over here corresponding to the for the energy component from ground resolution cells of water, okay, then in the first case, if I demarcate over here by the green line, This is the first part of river, okay, and this is the next part of river. So in the next part, water is the water turbidity in the water is more, while the first part is clear water. Okay. Now tell me, what will be the histogram for the energy components and how it looks like? Can anyone suggest me? Because see, here we can say that there are subclasses of water, and how we are categorizing the subclasses on the basis of turbidity, on the basis of characteristic of water, whether it is clear or turbid. By assuming the entire channel as a clear water, I have already plotted the histogram. Okay, in for the energy components which are required in red band, red spectral band. Fine. So it is a frequency versus energy plot. It's a histogram, and there we see that all the energy components are confined at a particular energy level. So they are concentrated. Why it is so? Because water is clear, and in the red spectral band, response in terms of like reflected energy from all the GRC of water, they are same. It means the same energy, nearly same energy is reflected back, and they are sensed at the receiver, at the sensor end. Fine. Slight difference could be there due to some minor changes in the internal composition of water, and due to that minor changes, we can expect this width over here. Now we have a second case where the major component is water, but there is a subclasses within the water on the basis of turbidity. And now I ask you to just let me know now what could be the histogram. I mean, what could be the frequency versus energy plot over here? What changes you can notice in this plot, and why it is so?
In turbid water, reflected energy will be more because of that soil particles in presence in the water. So it will be more narrow, this histogram.
No, fine. Just see. You are correct. When turbidity increases, so due to the presence of soil particle, the reflectance from the water will increase. Okay? So if we compare the reflectance from the water uh, in these two sections of uh, area that is covered by the water. So in the first section, we have a clear water, and let's say the reflectance is rho 1. Average reflectance I talk about, though you can notice the slight difference when we change the GRC location. But on an average, it's rho 1. And in the second case, we can assume rho 2. Fine. So first you need to analyze like which one is more. If we increase the turbidity, then what will happen? Reflectance will increase. Obviously, the rho 2 will be more than rho 1. And all the analysis we are doing at the red band. So obviously, within the red band, the sensor sends the reflected energy. We don't have a radiated component at the wavelength less than 3 micrometer. So it is clear we are dealing with the reflected energy component. So that's why I talk about the reflectance. So rho 2 is greater than rho 1. And we know that if reflectance is more, then what will happen? the reflected component will be more compared to the absorbed component. See, it is very clear. Irrespective of the location of GRC from water, the energy coming from the sun is same. Energy coming from the sun, and that is interacting with the water body, that energy is same, but the first case has less reflectance compared to the second case. Okay, so the water GRC reflect more in second case while less in the first case. Then again, if you notice this law of conservation of energy, where we derive how the energy interact, total incidence energy is equal to
Reflected, absorbed,
so it is absorbed plus ER plus
reflected, transmit.
transmitted. Fine. If we take the ratio, okay, so just see over here, incident energy, it is constant for all the GRC location. Okay, now it is redistributed. Fine. Now EI we are talking, let's say at the beginning we fix it. EI we are talking at red band. We are only interested in analysis in the red band. Okay, so in the red band, the incident energy is redistributed into absorbed, reflected, and transmitted. If we consider the second case, that is rho 2. If we consider the second case, then the reflected component is more. The EI is again constant, but reflected component is more. Then obviously the absorbed and transmitted component will be less. But when we consider the first case, this part is second case, while this part is first case. Okay, now when we consider the second case, okay, so ER2 it will be ER2 in the second case. Okay, so most of the corresponding to EI we have ER2, while in the first case, okay,
Sir, where you are writing that is not being displayed over here.
Yes, sir.
wait. Please wait. I hope now it is visible.
Not yet, sir.
No, sir.
Now let me know. Can you see the shared screen?
Yes, sir.
Yes, sir.
It has come, sir. Second case which you are writing now.
So in the second case, we have component ER2, the reflected component, while in the first case, we have ER1. Okay. And in the red spectral band, ER2 is more than ER1. Fine. Why it is so? Because due to presence of soil particle, the reflective capability of turbid water is more compared to clear water. So when the reflected energy is more from the second in the second case, then obviously energy sensed at the receiver will be more in the second case compared to the first. So E to I, let's say the index I for the second case will be more than the E1I. It is clear? So energy sensed from the water, GRC, but they are lying into two classes. Okay, clear, one class for the clear water, second class for the turbid water. Now, if you take the difference between these, like E2I minus E1I, okay,
सर ये इंसिडेंट एनर्जी कैसे डिफरेंट हो गई सर, ये समझ में नहीं आया।
क्या चीज?
सर ये E2I हाउ इट हैज बीन ग्रेटर देन E1I, सर थोड़ा सा कंफ्यूजन आ गई इसमें सर।
E2I, I am talking about this reflected. E2I means energy received corresponding to this reflected ER2 at the sensor.
ओके।
Or let me draw a schematic over here mentioning the nomenclature. Okay. This is a water channel. Okay. So one random GRC I have selected from the segment of clear water, while second I select from the turbid water. Okay.
सर स्क्रीन विजिबल नहीं है सर।
The corresponding to the first case, that is clear water, we have a reflected energy component ER1. Fine. So it is ER1, while in the second case, that is turbid, where I use the nomenclature ρ2 for the reflectance, so there we have a reflected component ER2. At the sensor, this energy goes towards sensor. So at sensor, the energy received corresponding to ER1 is E1I. I'm using this nomenclature. While for ER2, I'm using E2I. Correct?
हेलो सर।
हाँ बोलो।
सर आप जो कुछ भी लिख रहे हैं सर विजिबल नहीं है सर।
Is it for all of you?
Yes, sir.
यस सर।
Yes.
Yes, sir.
Now let me know. Can you see the screen?
Yes, sir.
Yes.
Yes,
There
sir.
may be some time lag if I write a sentence. If I write a word that might appear at your end after few seconds. Okay. So hopefully you can see the schematic where I mentioned the ER1, ER2, then corresponding to ER1 energy at the sensor is E1I and corresponding to ER2 energy at the sensor E2I. Can you see that?
Yes, sir.
Sir. Yes.
Okay. Now I hope through this workflow schematic, you understood this part. Okay. Now we have two subclasses of water. In the first subclass, we have the energy represented by E1I. When we analyze the differences among the energy components, like E1I, let's say mod minus E1I plus 1, we'll get delta E1. Though these E1I components are from the clear water, so delta E1 is very less. Reason is that the characteristic of water, okay, in the first case, that doesn't change significantly because, as I said, it is clear water. So energy may be slightly different, but they are very close to each other. And as it is plotted over here in this histogram. Okay, so let's say this histogram represent this first case first. Okay, it represent the first case. Fine. Okay, so in the first case, when we take the difference between energy from two GRC, so delta E1 component will be there, but this is very less because the characteristic of water doesn't change significantly from one location to another location within the clear water zone. Okay, and you can expect this type of histogram. But when we take the difference between energy component from the clear water and turbid water, E2I, okay, and you will get the difference E12. This is significant. Okay, why this is significant? Because there is a difference between the reflected ER2 and ER1. This turbid water, GRC from turbid water reflect more energy compared to the GRC from the clear water. Okay, and this, when you see this, but again, when we consider the third case, the differences between the pixels between the energy component from the turbid water, GRC from turbid water. Okay. That is delta E2. So again, delta E2 is very less because we consider in a turbid water zone, the characteristic of water doesn't change significantly. Maybe the turbidity level slight change due to which we have a different energy component, like E2i is different than E2i plus 1, and we have a difference delta E2, but again this is very less. So when we see the differences between the energy components from the GRC, water GRC, the highest difference you can notice when we take one GRC from the clear and another GRC from the turbid, delta E2. Okay, and when you plot based on this analysis, when you plot the histogram, now it becomes bimodal. Okay, there is a difference. The difference could be delta E12, and it is significant. And again, you have a second peak. Okay, this is another. Fine. So the first is for the clear, while second is for the turbid, and this is for the clear water. Okay. So I hope it is clear. This is a discussion on categorization of subclasses. Okay. But still, if you see over here, when we consider this part, so the first case and second case, in the first case itself, there are many energy components, okay, which are from the GRC of clear water, but they are very close to each other. They are different. Here I have given the number E1I. You can't say all the ith energy component are same from the clear water. They are different, but with a very slight variation. Okay, what we do?
सर स्लाइड शो नहीं हो रहा है सर.
अब आप सुनिए जो बोल रहा हूँ मैं. Is it for all of you? You can't see the shared slide. Can you see the screen where I have wrote where I have plotted the histogram? I have wrote the equations. That slide you can see. The shared screen you can see or not?
Yes, sir.
If you can see
Yes,
the
sir.
shared screen, if you can
Yes,
see
sir.
the shared screen, just listen. Okay. Just assume it as a kind of a PPT where I'm discussing the where I'm discussing the histogram, I'm discussing the equations. Fine. So if you see the histogram, it's bimodal. Okay. The first peak is from the clear water, while the second peak from the turbid water. Okay. Now in the first peak, if you notice, the energy components are different, but their differences are very less. When we go for analog to digital conversion, what we do, we assign a same number for all these energy components which are very close to each other. Why it is so? Because they represent the same class, same subclass, I can say. Because see, in the image, we are not interested to differentiate the clear water GRC. See, we are only interested to demarcate the clear water zone. We are not interested like how the GRC within the clear water are different. Okay, aim is to just analyze the water zone, okay, and only water zone. A further interest could be to just see the various subclasses of water in terms of whether it is clear water, it is turbid water. So now I hope you understand why we require analog to digital converter. The entire discussion, I'm establishing the concept that tells us like why we need to go for analog to digital converter where for lot of energy components, what we do, rather than storing them as it is, like in the See, again, I'm refreshing the screen. Please let me know if whether it is visible to you or not. Okay. Can you see now?
Yes, sir.
Okay. So fine. The case study, the example which that is selected for a given area of 5 kilometers square, okay, with 1 meter spatial resolution. The total number of ground resolution cell are 5 into 10 to the power 6. Okay. There are four classes, sorry, three major classes: vegetation, water, and soil. In the water, I considered two classes, so two subclasses: clear water and turbid water. Fine. And what I have done analysis of energy component CI, which are from the vegetation, which are from the water. So it is all EI component where I varies from 1 to 5 into 10 to the power 6. And through the discussion, we established the requirement why we need to go for analog to digital conversion. Because see, if you want to store each and every energy component, so we have a 5 into 10 to the power 6 ground resolution cells. All these energy components are different. Where I have already discussed that energy component from the vegetation, they are different, but variation could be very less. Similarly for water, similarly for vegetation, soil. Okay. So for each energy component, if you are going to store, just see, there are 5 into 10 to the power 6 different energy components. How many bits are required? Very large number of bits are required to store. Okay. And it can be solved like 2 to the power n less than 5 into 10 to the power 6 less than or equal to 2 to the power n minus 1. To solve this inequality, sorry, this will be okay. If you solve this inequality, the n value will be very high, and that number of bit is required to store each and every energy component. But this is not a requirement in our case. But see, when we consider from the remote sensing application perspective, what actually we want to just classify the vegetation class, water body, soil. Okay. So when we are only interested in the major classes and their subclasses, okay, then we need to establish a concept through which, rather than assigning each and every energy component a particular number, we assign the range of energy component a unique number. Why we assign the range of, let's say if I draw a line over here, and this is the minimum energy component and this is the maximum energy component. Okay, so if you start moving, what I said before, rather than assign a unique number to each energy component, we assign unique number to the range. Similarly, why we assign to the range? Because in the entire range, this energy belongs to the same class. Similarly, for the next range, when we say it's E max minus E mean, okay, if you divide it by this, if we can say this is delta, or this, let's say that delta is equal to 2n minus 1. You can say this 2n minus 1 is equal to E max minus E mean divided by delta. Delta means how much difference you want to keep over here to assign the same number. So on the basis of delta, you determine how many bits are required. Okay. So if you decrease the delta value, then what will happen? M will increase. Ultimately, let's say if we consider example E mean to E max, we have a total 255 segment, 256 segment if we start from 1. So first, second, third, fourth, till 256. Okay. Means you are dividing this E max to E mean in 256 segment. Then what we do, E mean the next energy, that is, we consider this part, it becomes E mean plus delta. For all these components, I'm just writing over here 1, 2. Let's say you assign a number 0. Then for the next segment, you assign number 1. For this, you assign number 2. And if you start from 0, the last you will assign number 255. So what actually we are doing over here, while converting from analog to digital format, for all E mean to E mean plus delta, all the energy components, you are assigning the same number. It means they are same. And if you see the transfer function which we are doing, it is like 0, then it is 1, then it is 2, it is 3, 4, like that. Okay, and we call this analog to digital conversion. And I hope you have understood why we require analog to digital conversion. If there would be the question like what is the reason why we need to add a step A to D converter at the sensor end, so hopefully you can able to explain in this way. Okay, and Is there any query? This is, don't confuse, 2 to the power n minus 1. N is equal to 8 bit, then this will be 255, because we are starting from 0 to 255. Okay. Now the last step at the sensor is sensor end is to assign a grayscale to the digital number. Okay. So in the given diagram, on the x-axis, we have an intensity range from 0 to 255 in case of 8-bit image. And one thing more I would like to highlight over here, the value of n that we calculate, the n is termed as radiometric resolution. Radiometric resolution means we are just analyzing like how close energy components we are distinguishing. When you increase the value of n, then what happened? You are decreasing the delta. You increase the n, we say radiometric resolution is improved, and by increasing the n, what we are doing, actually we are decreasing the delta value. Okay, and further we are differentiating this segment. Decreasing the delta means this is now very finer energy component we are assigning a unique number. Means we are interested in radiometric, closely monitoring the radiometric differences. Radiometric differences means how much energy which are sensed at the sensor. Okay, we are just narrowing that range. Okay, by increasing n, we decrease delta, and now we assign very narrow range to a unique number, and next range we assign a different number. So in the previous case, delta is large. Now let's say if we divide it into two parts, now the first part is given 0, second part is given 1. It is a further segmentation to analyze even the narrow differences in energy separately by assigning a different number. So that is the meaning of improving the radiometric resolution by increasing the n value. I'm giving you 5 minutes time to kindly prepare your note and just go through the discussion. We'll again resume our session at 12:15. Okay, so the last step is assigning a grayscale value to the digital number. In this two-dimensional plot on the independent axis, there are the digital numbers which vary from 0 to 255. And on the y-axis, we have a different sets of gray color. So this is a kind of linear assignment. Like again, if you see over here. So for the DN number 0, black color is given. For DN 255, white color is given. And for the intermediate digital numbers, on the basis of this transfer function, if let's say we select a 43 over here, so it will go like that. And using this transfer function, you need to just see that for 43, what is a set of gray color? Okay. So at the last step, by considering the digital numbers, the grayscale values are assigned by the linear transfer function. Okay. So in this case, the linear transfer function is considered. In the given figure A and B, the entire schematic is represented. How? By using a imaging system, the images are acquired in terms of digital numbers corresponding to GRC. Mechanism is given when we consider the sensor part over here, and it is depicted in figure B. So there is a mechanical rotating part, if you see over here. Okay. So mechanically rotating optics is there. So this is the mirror that keeps on rotating. And from the ground resolution cell, energy is falling on the mirror, and further this mirror is focusing energy on the sensor. Okay. So just see over here, it passes through over here. It is falling on dichroic grating that further divide energy into thermal and non-thermal part. And the non-thermal part is again passes through the prism, and again it is diverted after passing through the prism at a different energy band. In a different spectral band, energies diverted in a different direction, and further they are sensed. So these are the 5-channel sensing system. We can say 5 channels, 5 spectral bands are there. Each spectral band sense energy in its respective sensitivity zone. Okay, like what is the wavelength range where this particular sensor sense the energy. Now this is the sensor part, and further the energy sensed by each detector from the GRC. The analysis is done in the internal electronics that we discussed before, and a particular DN number for the GRC is stored on the storage device. Okay. So in this case, if we consider one ground resolution cell over here, and it is a 5-channel sensing system. So the energy that is coming out from this cell. Okay, that energy from the ground feature within this ground resolution cell. It passes through the mirror, and further in a different spectral band, they are sensed by the individual detectors, which are sensitive in that spectral band. And each detector has their own energy corresponding to this GRC. and corresponding to that, a DN number is assigned. So in case of 5-channel sensing system, one GRC, we have a 5 DN numbers. DN1, okay, DN2, DN3 to DN5. So in the next lecture, in the next slides, we will discuss about how many types of sensing system we have. Like for a specific type of sensing system, I'm discussing the architecture over here. How at the sensor end, processing is done from collection of energy coming from the GRC, okay, and how that energy is sensed by different detectors, okay, and further the storage of signal, storage of a DN number on the storage device. There is one more part that we need to discuss when we will analyze the differences between types of sensing system. What is the mechanism? Mechanism in terms of what type of sensing system we have, okay, and on the basis of sensing system, we'll see what is the mechanism of energy acquisition, okay. In this type of sensing system, as you see over here, there is a rotating mirror. It could be oscillating or rotating. So when you initialize the system, it starts sensing energy from a ground resolution cell. Then what happens? After some time, this mirror rotates. Now it okay. So at one particular epoch, this optics is focusing at one particular GRC for a certain time. Then uh, then after that, this mirror rotates to a new position, and now it focuses to the adjacent GRC. Similarly, it further rotates to a new location and along a particular line, okay, and Can you see the screen now?
Yes, sir.
Okay. So I'm discussing about the type of sensing system and how it operates. See, this red line indicate the flight direction. Okay, so the direction along which a aircraft that carry the sensing system is flying. So in this type of sensing system, there is a mechanically rotating optics. If I draw over here, so there is optics, okay, and this optics sense the energy. Let's say there is a ground resolution cell, okay. Okay, so ground resolution cell, the energy is going towards sensor system. First, that energy is passes through the mirror, okay, and now this mirror divert that energy to the, we have a dichroic grating over here, then further we have the prism. So role of these electronic components are to divide the energy into a different spectral band, okay. So so the energy that is sensed by the sensing system, it passes through the electronic component. And let's say if we select a 5 channel, in the previous case we discussed, okay. So 5 channels means we have a 5 detectors, separate detectors over here, okay. And the spectral band in which they are sensitive, that spectral band energy will be the output from this electronic component, and it will go through this, like from the prism. Let's say we have a 3 component, okay, while this dichroic grating is responsible for splitting the energy into thermal and non-thermal component, okay. So thermal component pass through this diachroic grating, while non-thermal component is that is reflected back. So the non-thermal reflected component passes through the prism, and they are further splitted into the separate spectral band, spectral energy component, and they are sensed by the individual sensor over here. We are interested over here how this, by rotating the optics, how we cover the entire area. What happens, like, let's say this is the this part. If you analyze this mirror, okay, so this mirror has its own in its normal, okay, so energy, which is the incident energy, if we say over here, it is reflected back following the Snell's law. We can say that angle of incidence is equal to angle of reflection. What happens if you rotate this mirror like this? Now this mirror has a separate different normal.
पोंगिया से बोलो मम्मी से बतिया तो नहीं
Some of you is unmuted. Could you please mute? Okay. So if you rotate the mirror, okay, now it has a different normal. What will happen? Now the angle of incidence, this will different. So in the first case, we have a GRC. Now in the second case, if you provide a rotation in this way, let's say it's anti-clockwise. So what happens? Due to change in normal in anti-clockwise direction, now this mirror will focus on the adjacent GRC. Further, if you rotate, its normal will change. Now the third GRC. In this way, considering the rotation from one end to another end, that is within a angular separation, what happens if I see over here? If you see over here, this is the entire FOV that is covered. I'm just making this box. This is an aircraft and it is flying in this direction. Okay. Within the aircraft, somewhere at the bottom, we have a sensing assembly. Okay. And this sensing assembly part is depicted over here. This portion is draw over here. That mention how the mechanical rotation is provided to the optics to scan the different ground resolution cells along a line, and we'll call it scan line. Okay. So this is the scan line, and it is a line along which, by mechanically rotating the optics, the sensor system acquire the GRC, acquire the energy from the GRC to generate a equivalent distal number. So in this type of sensing system, what we have a mechanically rotating mechanism through which we are rotating the optics. By rotating the optics, its normal changes. And when the normal changes, it focuses at the different ground resolution cell. And as you can see over here, okay, so that in one particular rotation, if we see, if we restrict a rotation from, let's say, if this is the somewhere this line is considered as a reference, this angle is, let's say, minus some theta value theta1, and this will be plus theta1. So minus theta plus theta2, minus theta1 to plus theta2. Within this two extreme end, and total it will be theta1 plus theta2. Rotation is provided to the optics, okay, at a particular angular speed, so that all the ground resolution cell along this scan line, they are sensed by the detectors. These are the detectors. Okay. So by considering one particular GRC, the energy which is coming out from the GRC, that energy is available in wide spectrum. Okay. That energy passes through the prism, passes through the optics. Now they are focuses to the diacoic grating. Okay. This is responsible for splitting the energy between thermal and non-thermal part. Thermal part is allowed to, that is transmitted, while non-thermal part is reflected back towards a prism. Now when that energy passes through the prism, it further split energy into the spectral component. And now those individual spectral components are sensed by the corresponding detectors, which are sensitive in that spectral band. Okay. Few concept, or we can say few terminology you need to understand over here. The first one is, like if we see over here, at a particular fixed time, like see we are providing an angular rotation to optics to acquire the new position. Okay, because see, if at a particular angular speed v, when we rotate the optics at a particular epoch, let's say sometime t, it focuses to a GRC, ground resolution cell. And let's say for delta t time, very small time, it sends the energy from GRC. Now, due to the angular speed, due to the rotation, after delta t time, at t2, now it focuses to the adjacent GRC because its normal changes. At t3, it focuses to the next GRC. But at least for delta t time, the optics is optics is receiving energy from one fixed GRC, and this delta t is called as dwell time. Okay, and there is a IFOV, we call it, it is represented by beta, instantaneous field of view. So this IFOV is dependent on the sensing system architecture as well as detector. IFOV beta determine the GRC size. Okay. So this IFOV, this beta talks about what is the focus area. When optics is focusing at a particular location, what is this beta angle? What is the solid angle within which that optics is, collecting the energy from the ground? Okay, and it further determine the size of GRC. Like within that solid angle beta, energy is being collected by the optics from the ground element. Okay, so we have a term IFOV, that is instantaneous field of view. So in a fixed IFOV, for the dwell time delta t, the mirror focuses at GRC, okay, and sense and collect the energy. Now IFOV location changes to the next due to the angular rotation of optics. Now from the next GRC for delta t time, energy is again sensed. So now I hope you understand what is a mechanism through which the GRC along a line that we call a scan line are sensed and DN numbers are generated. Similarly, now the aircraft moves to the next location and the next line is sensed. Further, it moves to the next location and further the next successive consecutive scan line is sensed. So in this way, the entire area is imagined. And corresponding to the GRC, DN numbers are generated in each spectral bands. Okay. Now there is a small query. Let's say the size of area that is sensed is 2 kilometers square. Okay. And the 2 meter is the spatial resolution. We have a square GRC and the spatial resolution is 2 meter. We are using 5 channel, that is 5 spectral band to sense that entire area. Okay. So how many digital numbers are recorded? Total number of DN. How many they are? Solve this problem and let me know.
Sir, 5 into 10 to the power 6.
25 lakh.
How you solve this? Through the mechanism, I am discussing this part. Okay. Carefully see that. Our aim is to just know how many DN numbers are there in the image. Okay. So first we calculate how many GRC we have. Okay. To calculate the GRC, what we do, we divide this 2 into 10 to the power 6 meter square. It will be, okay. And this is the 4 meter, then area will be 2 meters, so area will be 4 meters square. Fine. The total GRC comes out to be 5 into 10 to the power 5. Is it okay? So 5 into 10 to the power 5, total number of GRC. Now we see using the 5-channel sensing system, for one GRC, how many DN numbers are generated. So just look at this architecture. I am considering one GRC over here. Okay. Right, let's say this is the first GRC. Energy in a wide spectrum is reflected back, reflected or radiated, we can say the outgoing energy from GRC first is sensed by the optics over here in its IFOV. So within the IFOV, from the ground within a GRC for delta T time, that is dwell time, the energy is sensed. Okay. Now that energy passed through this electronics component. Now this electronic component, this is the 5-channel sensing system. So this electronic component just after the optics, that system divide in a total total energy at the sensor into 5 parts. Okay. Now the individual part of energy in which that detector is sensitive, so they are sensed corresponding to one GRC. 5 energy components are sensed. So they are E1, E2, E3, and E5. 5 energy components are sensed in a different spectral band. Okay? And spectral bands are chosen on the basis of sensitivity of detectors. And this the intermediate component divide the total energy received at the optics into the 5 spectral component. Okay? Within the given within the selected spectral band. Okay. Now they are sensed, so corresponding to one GRC, 5 different energy elements are energy components are sensed, and for each component we assign a DN number. So DN1, DN2 to DN5. So one GRC we have 5. What you need to do, you need to multiply it by 5. So 25 into 10 to the power 5 DN numbers are generated. Let's say if it is 8-bit image, so what is the size of image? Eight-bit image means I talk about when this is the energy components of the analog signal. By using A to D converter, we are using radiometric resolution 8-bit. Convert energy signal into the digital number. 8 bits are used, which is the radiometric resolution of the system. For all channels, 8 bits are used. Okay. So, what is the size of the image? Obviously, when we analyze, like for energy signal, how many bits we are using to store it in terms of digital number, that gives you idea about how much storage is required. So if 8-bit is used to store the data, then what will be the size of image?
So size of image in terms of what?
In terms of bits. How you measure the size of a JPG image? Total number of DN is equal to 25 into 10 to the power 6. To measure the size of the image, you need to see for one DN, what I said before, when we are going to store a digital number that is given in decimal number format, what we require? We require a binary equivalent, because in a binary number system only the information is stored on the storage device. So for a given particular digital number that is in a decimal number format, for one DN number, how many bits we are using to store on the storage device? It is 8-bit system. So we are using 8 bits. Fine. So how many total bits are required to store the total DN number? Need to multiply 25 into 8 to 10 to the power 6 bits. This is the total number of bits which are there to represent the image. Obviously, this much to store these bits, we require the equivalent storage space on the disk or on the storage device. So this is the size of the image. Size of image is represented in terms of bits. Bits, or you can write in terms of bytes. Okay. So it will be 25 into 10 to the power 6 bytes, or 25 into 8 into 10 to the power 6 bits. This will be the size of image. Okay. If I would like to, if let's say you need to write a generic formula to compute the size of image, then what are the parameters? Parameters are, they are total number of GRC, ground resolution cell, multiplied by number of channels, number of spectral bands, multiplied by the radiometric resolution. That is how many number of bits. Okay. So there is a problem given for computing the size of image. You require the input information in terms of how many total number of pixels are there in the image, pixels in terms of how many ground resolution, how many picture elements are there, okay. How many spectral bands are there in the imaging system, okay, and what is the radiometric resolution, how many number of bits are used in analog to digital conversion, and you need to multiply them to get the size of the image. I hope it is clear. If there is any doubt, you can discuss. Otherwise, we can stop our meeting session over here.